Okay, good morning. We start the lesson. The topic for the lesson today is matrix powers, but I realized that there is something missing from the last session. We didn't have time to cover it. So if you don't mind, let me first cover that. So here I want to start with this example actually today. Consider the following matrices A and B. We want to calculate the trace of the product of A by B or B by A. So we want to calculate these two. So in principle, you know that AB is not equal to BA, but there is something interesting happening that will be the content of the next theorem, that the trace of AB is always equal to trace of BA, even if AB is itself not equal to BA. Okay, so let us actually understand this. So the problem here is a matrix A is given. So A is equal to 2, 3, and minus 1, 0, 2, and 1. And we also have matrix B, which is 0, minus 1, 1, and 1, and then finally 2 and minus 3. Okay, so let me calculate the trace of AB first. To do this, I have to multiply A by B. So A is 2, 3, minus 1, 0, 2, 1. I multiply it by 0, minus 1, 1, 1, 2, and minus 3. And I calculate this. Is it possible to multiply? Let us review a little bit. So there are 2 rows and 3 columns in this matrix. There are 3 rows and 2 columns in that matrix. So it is possible. And the result will be a 2 by 2 matrix. So I partition these 2 rows, partition these 2 columns, and I start multiplying. So let us just do it in our head. So 2 times 0 is 0. Forget about it. 3 times 1 is 3, minus 2. So it is 1. And I will take this one, multiply it here. Minus 2, 3 plus 3 is 4, yes? And then I take this row and multiply it here, 0, 2, and 2, which is 4. And then I take this one and multiply it here, 0, 2, and minus 3 is minus 1. Yes? Can you confirm my calculation, yes or no? Was it right? Let us see. So let me calculate the trace. Do you remember what was the notion of the trace?
Yes.
So what's that? Yeah.
You add all the
entries on the end, which is in this case 0, yes? Okay, let me now calculate B times A. It would be a different matrix, of course, because here you see this is 0, minus 1, 1, and 1, 2, and minus 3. I am supposed to multiply it by 2, 3, minus 1, 0, 2, 1. And then I will see if it is possible. This is 3 by 2. This is 2 by 3. Yes? So it is possible, but the result is a 3 by 3 matrix, yes? So I will partition these 2 rows and these 2 columns, and then I start multiplying. So this row by that column, 0, 0 is 0. This row by that column, 0, minus 2. This one by that one is minus 1. And then this one becomes 2. This one becomes 5. This one becomes 0. And then I have 4. And then I have 6, minus 6, 0. And then I have minus 2, minus 3, minus 5. Yes? So you see that this is quite a completely different matrix. This was 2 by 2, this is 3 by 3. But the point is that still the trace is the same number. Okay? So if I calculate the trace of BA, the answer is again 0 plus 5 plus minus 5, which is 0. Yes?
I'm wondering, for the theorem it says that A and B have to be square matrices of the same order, but neither A nor B in this problem was square matrices.
No, that was probably my mistake. I have to modify the theorem. Yes, that's good. It doesn't mean that for the square matrices it doesn't work, but it is not necessarily square matrices. So I was a little bit careless. Thank you for pointing this out. I will fix it. Thank you. But anyway, I want you to see that this is a little bit, so you might think that is a coincidence, but we can prove that no, this is not a coincidence. That is always the case. So it is extremely important to know that if even if AB is not equal to BA, but the trace of AB is still equal to trace of BA. Okay. So why this is the case? So let us go back here. So as you mentioned, so this theorem, we can say that if A and B are so that they can be multiplied from both directions in this way, for example, yes? In that case, the trace of AB is always equal to trace of BA. We want to prove this. And of course, the content of the theorem is telling you that note that the above theorem is true, even if AB is not equal to BA, which of course, usually it is not. Okay, so how do you think we can prove this in general? So let me just, for the time being, modify that. So I would say that let A, B, and M by N, and B, B, and N by M matrix. Yes, this is clear, yes, because if A is M by N, so as you mentioned, I want to have a matrix, let me write it P times Q, PQ, P by Q. If A is supposed to be able to be, so if I'm supposed to be able to multiply A from the left, P and N should be the same. If I am supposed to be able to multiply B from the left, Q and M should be the same. So if this matrix is M by N, that matrix should be N by M. Okay, so that's why I'm writing it. So let A be an M by N and B be an N by M matrix. We show that the trace of AB is equal to the trace of BA. Okay, how can we prove that? So I hope that you agree that this is a non-trivial result, yes, because matrix multiplication is a little bit involved process. And we know that in principle AB is not equal to BA, but I want to show that suddenly what happens on the main diagonals, the sum will remain the same, okay? So how can we prove that? I start from the left-hand side. That is trace of AB. But what was the definition of the trace? What is this product? A is M by N. Yes, this A is M by N. This B is N by M. So the product will be an M by M matrix. So if I want to calculate its trace, I have to add up all the entries on the main diagonal of the matrix AB. Yes? Okay, so main diagonal of AB, let me write it as AB. Do you remember main diagonal has this property that the row index and the column index are the same. And then I have to run I from 1 up to where? The order of the matrix AB. But A times B is an M by M matrix, so it goes up to M. Yeah, so it is important because you cannot just write, and so you have to introduce that the order of A is M by N, so the order of B has to be N by M in order to be able to define AB and BA simultaneously. Then if I start writing trace of AB, I need to realize what is the order of AB. It is not hard. The order of AB is M by M, and I have to start adding up all the entries on the main diagonal from the number 1 until the last one. In this case, the last one is the number M. Yes? Okay, so I copy and paste this sigma, but then you need to remind yourself about the formula for the sigma here. So this is a product, and I am interested in one entry of the product. So that is another sigma, do you remember? So I expect to be able to fill it up. So what should I write? I want to write a sigma for the product entry II. So what should I write? I need to choose a counter. So let me choose counter 1. It always goes from 1 up to where here? You don't know? Yes? N, the number, because N is in the number column here. And then you start with A. You have 2 indices to fill up here. And you have B, you have 2 indices to fill up here. So what are these 2 indices for the first one? That's important to know how to write this sigma. So what are the indices for the first one? It starts with the I index, which is I, ends with the counter. The second one starts with the counter, ends with the column index, which coincidentally here is again I. Yes? Okay. I know that my goal is to be able to replace B and A. Of course, it doesn't matter here because these are numbers. If you want to, you can replace them. But if you replace them, so what I do, I will interchange the sigmas. We learned that if I have consecutive sigmas, I can interchange them. So it becomes K goes from 1 to M, and then sigma I goes from 1 to, sorry, K goes from 1 to N, I goes from 1 to M, and then I can write it the other way around. Ki and Ai k. By the way, it is extremely important this because you know that there is no difference between this and that. How should I know I have to interchange? Because now, if you look at this part, what can I write instead of that? So you see this should look familiar to your eyes now. This combination is familiar. So you have a sigma, you have 2 matrices involved. The middle indices are actually the counter, and then I have one index here, another index there. So I can collect it back in the form of a product. Okay, so let me copy and paste the first sigma here. And then what I do, okay, can you tell me what can I write about this? What can I write eventually? Yes, BAKK. Yes. But what is another name for this sum? Can you feel that? Because KK means you are working on the main diagonal of this matrix BA, and then you are adding them from the first entry to the nth entry. And that's exactly correct, because if you multiply B by A, B is n by m, A is m by n, so really it is true that the BA matrix is n by n, and then you're running it from the first to the last, so this becomes exactly equal to the trace of BA, and that is exactly equal to the right-hand side. So this is the rigorous proof. So this was not a coincidence, because we were able to show that in all cases this can happen. This happens. Yes, is that clear? Okay. So I want to talk about this example now here, example 103. So here you have square matrices, of course, A, B, A, and B of order n. Do you think you can find matrices A and B of the same order n so that if you write AB minus BA, it becomes the identity matrix of order n? Okay, so this is probably the first example that you really need to understand what is the notion of a trace. Okay? So let me describe the problem on the board here for you. So before doing that, let me ask you a question. For example, let me ask this question. A is 2 by 2, B is 2 by 2. Do you think there are 2 by 2 matrices so that if you calculate this, it becomes the identity matrix 2 by 2? Let us try to solve this problem directly without any other. So how do you think about the problem? The question is that, do you think it is possible to find a pair of 2 by 2 matrices A and B so that when I calculate AB minus BA, it becomes the 2 by 2 identity matrix? So assume that we want to answer this question and you don't know anything about the relation of this lesson to what I just told. Now, how do you tackle the problem? The problem here is the harder version of that. Why? Because here I'm asking about only 2 by 2. The question is asking about all n by n matrices. So even if you can find A and B for 2 by 2, then the question is that can you find 3 by 3 matrices with this property that this becomes I3? If you can find them, then I will ask a 4 by 4. So the problem becomes harder and harder. Okay, so let us just try to understand this problem for this case, 2 by 2. Do you think it is possible? Yes?
I think it's possible.
Okay, if you say possible, it means that you need to provide me a pair. To find that pair, that's a good idea. If you think it is possible, let us find that pair. Okay? So let us find that pair. So I will say that, okay, A is a 2 by 2 matrix. I don't know what that is, so let me put 4 unknowns for it for the time being. And then B, I don't know. For example, let me write it as C, D, E, F. Yes? And let me try to find them. How many unknowns I'm encountering here? I have 8 unknowns because A is not known, B is not known, so I should be able to find them, yes?
But you had CD twice.
Okay, thank you. A, B, C, D, E, F, G, H. Thank you very much.
You're welcome.
Okay, so then what you do, you start calculating AB minus BA to see what happens. So AB is A, B, C, D. I multiply it by E, F, G, H, and then multiply minus the other way around. E, F, G, H, and then you have what? A, B, C, D. Okay, so what happens here? This becomes AE. So let me calculate it. AEB plus BG. The other one becomes AF plus BH. The other one becomes CE plus DG. And then CF plus DH. Minus, I do something similar here. It becomes EA plus FC. I multiply E by B, EB plus FD. And then I have GA plus HC. And then I have GB plus HD. Yes? And I hope that you agree that if I increase the dimension of the matrices, the calculation becomes messier and messier. Let me double check everything, yes? So AEBG, AFBH, CEDG, okay, that's wrong. CF plus DH, I don't know what I have written here. Yes, CFDH. No, that was correct. AE plus BG, that was correct, sorry. AF plus BH, and then I have CE plus DG, CF plus DH. That's correct. Then I go there. EA, FC, EB, FD, GA, HC, and then GB, HB. That's HD, that's correct. Everything is correct. Okay, so let me now, so you see it is not that easy to answer the question. Now, if I subtract them, this one minus that one, EA and AA are cancelled, so I am left with BG minus FC. And then what I do there, it becomes AF, nothing is simplified here, so I have to write all of them. AF plus BH, I don't know, minus EB minus FD, and then I will subtract these two, so it becomes CE plus DG, nothing is simplified, minus GA minus HC. And then when I subtract these two, one of them of course is cancelled, but then I will have CF plus minus DH. So this is cancelled, minus GB. That is what I get. I want you to understand, this calculation becomes very involved if I go to 3 by 3, 4 by 4 matrices, etc. Okay, so in principle, if I have two arbitrary 2 by 2 matrices, if I calculate this, I will get something like that. But is it possible that this matrix turns out by fine-tuning these A parameters? Can I make this to be the identity matrix? The identity matrix 2 by 2, is it possible to make this equal to this? Is that possible? If it is possible, then it means that you need to be able to fine-tune these parameters so that this becomes 1, this becomes 0, this becomes 0, and this becomes 1. One way is to start working things out to see if you really can find that. But if you are observant enough, you immediately realize the answer is no. Okay, one way is to, because first of all, you shouldn't expect to be able to solve the problem, because how many unknowns I have here? 8. But how many equations I will get at the end? 4. Equality of each one of them gives me 1 equation. So I have 4 equations, but I have 8 unknowns. So it seems that you have infinitely many so you have more degrees of freedom. When you have more degrees of freedom, you think that you might have infinitely many solutions. But in this case, this is actually the opposite. There are no solutions to this system. Do you see why? And if you see why, that is the key point to understand that you can say the same thing for higher order matrices. Do you see why this is not possible? Yes?
Because in the first one, in the first diagonal, or in the diagonal, is BG minus FC.
Yes?
And the second one is CF minus GB.
Yes?
But both of them needs to equal 1, but they can't because they are on two separate sides of the subtraction.
Yeah, exactly. So this means that BG and FC, I have BG minus FC, CF and FC are the same, GB and BG are the same, but this number and that number are not the same, they are actually opposite. So whatever this number is for any choices of these parameters, that number would be the same but the opposite one. So, but it's not happening because here I have two same numbers, 1 and 1. So you shouldn't think that you shouldn't waste your time in finding those parameters. With this simple argument, we realize that the answer is no. Okay? But do you see what was the point here? Do you want me to repeat the same process for a 3 by 3, 4 by 4 and see that this is not possible, or you have a better argument now? So now let us go back to the problem. The problem is this now. The problem is that, is it possible to find square matrices of any order, say order n, with this property? I hope that you realize the answer is supposed to be no, but how we can go for the argument. I would say that if you think it is possible, then this matrix is equal to that matrix. So this means that the trace of this matrix should be equal to the trace of this matrix, yes? If you say that you can find A and B with that property, then you have to admit that the trace of the left is also equal to the trace of the right because they are essentially the same. But do you remember we had one property that the trace of the difference of two matrices is equal to the trace of the first one? This is an important property of the trace minus the trace of the second one. Yes? But what is the trace of IN? What is the trace of IN?
It's 2.
No, IN. I2 is 2.
Oh.
IN is
N.
N because you have N of them, so it becomes N. But today we just learned what is this subtraction?
0.
0, because we just learned that it doesn't matter. A trace of AB is always equal to trace of BA. So the left-hand side becomes 0, the right-hand side becomes N, but this is a contradiction, yes? Because N is the order of your matrix, it cannot be 0. So you see, this is a very, very simple argument, yes? Which works for all cases. Yeah, is that clear? Okay, now we go back to slides here. That I want to talk about, and then we go to the lesson for today. So cyclic property of the trace. So if A, B, and C are all square matrices of the same order, so the trace of ABC is equal to trace of CAB is equal to trace of BCA. That's called cyclic because I will actually describe it here for you on the board. Why it is called cyclic? Because if you start from A and then, for example, go to, I don't know, go to B and then go to C and then go back. So this is like a cycle. Okay, so when I say trace, I can start, for example, from A and go in this direction. It becomes ABC. But I can start from B and go in the same direction. It becomes what? BCA. And I can start from C and go in the same direction. It becomes what? Trace of CAB. Okay? So I'm claiming that all these are equal. So that's called the cyclic property of the trace. So you see, I haven't replaced A and B. So the way that I read is the same if I start from A all over again. So it's A, B, C. If I start from A, B, C. If I start from A, B, C. So if you respect this cyclic way of writing, you will actually get the same answer for the trace, even though the matrices inside might be completely different. The reason is that we don't have commutativity. So if you reorder them, there is no guarantee that this matrix is equal to that matrix. But why do you think this is true? For example, let us, I don't know, concentrate on these two. Why do you think these two should be the same? And then you can argue in the same way that all of them should be the same. Yes?
Let's say that you were going to put brackets around BC.
Okay, so let me just write. So you start from here, trace of A, B, C. You know that matrix multiplication is associative, so it is up to you how you want to group them. So what Robert is saying is that you put a pair of brackets around B and C, okay? Then it becomes trace of A, B, and C. Okay, then what?
And then you do the same on the second one, trace of BCA. And since we can see BC as its own matrix.
Okay, exactly. So you don't need to do that. So that's I agree with you. So you can call this and you can give it a name, for example, and then you have A and curly B, but you know that we just learned that you can interchange them. Yes. So what happens? It becomes trace of this curly B and this A. Do you agree? This is exactly the content of the theorem that we just talked about. Okay, but then you can take this curly B away and put this back. So this becomes the trace of what? BC times A. But do I need pairs of brackets? No, because it's associative, so I remove that one. So it becomes BCA. So if you compare ABC with BCA, we actually were able to prove this one. So that's exactly the same thing, but if you use it in that way, this becomes a cyclic property of this. And of course, you can increase it for more than 3. For example, if I have trace of A, B, C, D, I can write it as trace of move A to the second position, B to the third position, C to the fourth position, and D to the first position. That's true. And then you can do it, for example, once more. You can move this to the second position, A here, so A, B, and this one. So A, B, C, D. So these are all the same. So if you do it in a cyclic way. Is that clear? Okay, so here, I don't know how many of you are actually solving the problems, because whenever I write recommendations, I really ask you to do the problems as much as you can, okay? So there are some good problems here, and I always update them, okay? So, and the updated version will be on Google Classroom. So this is a very important topic. So we want to talk about these powers of a matrix. And of course, now we start with only non-negative integer powers. Okay, so it means that the powers of a matrix that you expect to see are 0, 1, 2, 3, 4, etc., etc. Okay, just tell me, so what do you think, if I want to define, how do you define in non-negative integer powers of a matrix? Because you know that, you might say that, okay, powers are clear. But because we have a new object in mathematics called matrices, we are constructing the new algebra on them, so we have to redefine everything. Yes?
So would it be you multiply the same matrix by itself n number of times?
N number of times. So what is your opinion about a to the 0?
Maybe that would be just a 0. Actually, I don't know.
So you can think about it a little bit. So, okay, first of all, I want you to see that it is not possible. This is the natural definition. What actually Rocco mentioned is correct. Yes, you want to take that matrix. If I say, for example, a to power 3, I expect you to do the same thing as powers we did with numbers. Yes, you take the matrix, multiply it by itself 3 times. But first of all, tell me, is it possible to raise any matrix to power 3? Or there is a class of matrices that we can raise them to power 3? Or let us make it to power 2. Power 3 means multiplying by 3 times. Let us just talk about power 2. Yes?
Isn't it only possible with square matrices?
With the square matrices. So this is extremely important. If I have a rectangular matrix, I cannot actually raise it to power, multiply it by itself. For example, if I have A 2 by 3, which is a rectangular matrix, if I want to multiply it by itself, it is not possible because these numbers are not the same. So that is one thing that you need to know. The topic of powers of matrices only makes sense if I am dealing with square matrices. In that case, what Rocco said is actually completely good and natural, yes? So it means that when I have a square matrix and I want to raise it to power 3, what can I do? I take the same matrix multiplied by itself 3 times, yes? And if I want to raise it to power 2, multiply it by itself 2 times. By the way, tell me this one. Do you think, which property is involved here in order to be able to define this? I can define a squared. I read exactly the same thing, but I want you to understand what is the meaning. So this means that a multiplied by a, okay? But when I write a to power 3, what was your intuition? The intuition is actually correct. That is the definition. But there is one property heavily involved here. Which property is involved here? Because if that property, so you know that we lost commutativity, but we have associativity, we have actually distributivity. One of these that I mentioned that we have is really involved in order to be able to do this without ambiguity, yes?
Is it distributivity?
No. Distributivity is always the case that you have two different operations. Here we have one kind of operation, and that's multiplication. But the question is that this one and that one, if they are not the same, then I am in trouble, yes? So it depends, because when I multiply a by a first, it becomes a squared, and then I multiply a squared from left to a. If it is not the same as this one, then I am in trouble, because here this becomes a squared times a, and this becomes a times a squared, yes? And so you see that I am interchanging them apparently, but I know that commutativity is lost. Okay, the good point is that associativity is not lost. So this means that because of associativity, I can show you that this and that are the same, even though it seems that I am commuting them. I am not using commutativity, I am using associativity. That's good, except for this one, everything is very natural and normal. So if I want to calculate a to power n, n is a positive integer, then I multiply it by itself n number of times. But what do you think is a good natural definition? Because we are defining things here, but we are defining them in a natural way. So what is a good definition, do you think, for a to the power of 0? Because what is in the back of our head is comparing it with numbers. Yes, I don't want to destroy everything we have learned so far, because we want to learn about matrices. So we want to be able to actually do something similar to about numbers. So what's a good definition? So how do you compare it? You usually compare it probably to 2 power 0, yes, a to power 0, if a is a number. How a to power 0 is defined? 1. So here, what do you define, do you think?
Identity matrix.
Yes, because I told you that the identity matrix playing the role of 1 in matrix algebra. So that is defined to be the identity matrix. Yes, is that clear? Okay, so let us go back to slides here. So as you just mentioned, so if I have a to power n, a is a square matrix, a to power 0 is defined to be im. M is the order of my matrix. So assume that A is an m by m matrix. If I ask you to raise it to power 0, by definition you answer im. And if I ask you what is a to the power of n, you will tell me that I multiply a by the previous power. So this is definition, inductive definition of the powers. Yes?
What do you mean by defined inductively?
Yeah, exactly. That is what I'm saying. Inductive, and we know a little bit of induction now, mathematical induction. So it means that if I want to define an, so if I want to say what is a2, then a2 becomes what? A times a. If I ask you what is a3, I will tell you a3 is a times a2. And if I ask you what is a4, I would say that this is a times a3. So it means that if I want to answer what is a4, I have to already calculate a3, and in order to calculate a3, I have to calculate a2. So this way of defining is called inductive definition or recursive definition. Anyway, might be I am making it a little bit more complicated, but that's the rigorous way of defining things, okay? But what you said is exactly correct. The first example I want you to do is actually, I want to pause recording. I want you to do this yourself and then compare it with the squares of these numbers. Are they somehow related or not? Okay, so just do this example for me now. Okay. So I think this is very simple. Yes, if I ask you to calculate I read it the same. I read it as a squared. So what happens? It means that you have to take a and multiply it by itself. it has nothing to do with raising these numbers to power 2. Okay, so don't get confused. Okay, so what I do, I will take this matrix and multiply it by itself. Okay, so then what is the answer? I take this row and multiply it by that column, so 4, 4, 8. And then I take this row, multiply it by that column, minus 2 minus 3 is minus 5. And then I get minus 8 minus 12, it's minus 20. And then it's 4 and 9 is 13, yes? Yes, am I right?
Yes.
Okay, and then you see that again, compare it. You see, if you just raise these numbers to power 2, is nothing, it's not exactly, it's not at all like this. Yes, it is 4, 1, 16, and 9, which is not the same. So when I say raise it to power, it means that you multiply it by itself. Okay, so let us go here and read this remark. So power of non-square matrices are not defined, as we discussed later, previously. So what is this one? It's very clear that if I have a zero matrix, of course, zero matrices could also be rectangular. I am only talking about the square zero matrices. It is clear that if I raise them to any power, the answer becomes a zero matrix. Yes, if you take the zero matrix multiplied by itself, because all the entries are zeros, so the resulting result will be the zero matrix. But this is a very also important. The identity matrix to any power is equal to the identity matrix. Why? Yes, why is that? Because we learned that any matrix multiplied by the identity matrix is equal to what? Is equal to the same matrix. So if A itself is the identity matrix, then identity matrix times the identity matrix remains the identity matrix. And then identity times identity is identity squared equals to identity. And then you can also understand that if I raise I to any power, it becomes the same identity matrix. Okay, I want you to do this exercise now. I want to wait for you, by the way. Okay, so these three problems are of the same type. Okay, so let me make this a little bit smaller so that you can see them. So I want to wait for you to solve these three examples for me. Okay, could you solve the first problem? Yes, at least I think the problems are actually very straightforward, but let us see how it goes. The first one, this is, of course, I want to improve your skills once, but the other thing is that I want you to see that there are no zero entries here, but suddenly these numbers are in a way that when you raise it to power 3 and everything suddenly becomes 0. Okay, so these kinds of things you should expect when it comes to matrices. So let us solve the first problem here. So here, let me solve it here. So if I want to calculate a to power 3, I don't know, you can calculate a multiplied by a squared. Yes, so if I want to calculate this, first I have to calculate a squared. Let me start with a squared. A squared means that I have to multiply my matrix by itself. So it is 1, 1, 3, and then I have 5, 2, 6, and then I have minus 2, minus 1, and minus 3. I multiply it by itself, 1, 1, 3, 5, 2, 6, and minus 2, minus 1, minus 3. So if I multiply these two matrices, so let us just do it. The first row by the first column, so 1, 5 is 6, minus 6, 0. I take this row by that column, 1, 2 is 3, minus 3 is also 0. I take that row by that column, so 3 and 6, 9, that is also 0. And please check my calculations. If I am doing something wrong, please let me know. So it is 5, 10, 15, it's 3, yes? And then 5, 4 is 9, minus 6 is also 3. And then I have 15, 12 is 27, minus 18 is 9. 27 minus 18 is 9, yes? And then I go here minus 2, minus 5 is minus 7, and this is positive 6 minus 1, minus 2 is minus 4, 3 is minus 1, and then I have minus 6, minus 6 minus 12, it's minus 3. I don't know, can you confirm that what I have done is right? Is that right?
Yes.
Yes. Okay, and then we go actually to to the 3. Okay, so for a to the 3, you have two options. Either you can write a squared on the left and multiply it by a once more, or you can write a on the left and multiply it by a squared. Apparently, you should expect that you might get different results, yes, because these are different matrices. But because of associativity, it is guaranteed that no. In any way that you do it, the final result will be the same, even though the intermediate steps are different. So I don't know which way you want to do it. So let me take a again and multiply it by a squared. You could take a squared first and then multiply it by a. So what is a here again? 1, 1, 3, 5, 2, 6, minus 2, minus 1, minus 3, and I multiply by the matrix that I just found. If I have done everything right and if the problem is correct, I should be able to get the 0 matrix here in this case. There is no guarantee that this would happen, but some matrices are like this, even though they are non-zero matrices. By the way, this is very surprising again. You see, if I give you a to power 3 is equal to 0, what can you conclude about a? A is 0, but this is not the case. You see, a to the power is 0 matrix, but the matrix itself doesn't have even one single entry of 0. Yeah? So that is important to understand. These things can happen in matrices. Okay, here we have to be a little bit more careful. I take this row and multiply it by that column. So 1 times 0, 0, 1 times 3, 3 times minus 1, it is really 0. And I take this and multiply it by here. What happens? So the first one times that is 0, this is 3, this is minus 3, so it is 0 again. I will take that one and multiply it here. 1 times 0, 0, this is 9, minus 9, that is also 0. So take that one, multiply it here, it is 0. I take that one, multiply it here, 6 minus, that's also 0. Take that one, multiply it here, that's also 0 because that is 18 minus 18. And then that's 0 and that is 0 again. Minus 3 plus 3 is 0. And then minus 9, okay, that's also 0. Yeah, you have to convince yourself that I have done things right, but this becomes the 0 matrix 3 by 3. So that's also good to know that a to the power of 3 is 0, but the matrix A itself has nothing to do with the 0 matrix. These things can happen. This is a very standard but simple question. So how should I do this? Yes?
You start by multiplying a by a.
Yes, and then put them in this equality, and then you will get two unknowns and two equations. Then you will find the alpha and beta. So let me write this again here. So I put everything here. So a squared means multiplying a by itself. So it becomes 1, 2, 2, 1 multiplied by 1, 2, 2, 1 is supposed to be equal to alpha times a. A is 1, 2, 2, 1 plus beta times I. But which identity matrix do you think it will be here? It should be a 2 by 2 because otherwise it is not defined. So, and then identity matrix 2 by 2 is something that you have to have in your memory, okay? It will not give you in the text of the question. Okay, and then you need to find alpha and beta. So I do the calculation on the left. I take this one, multiply it here, 5, and then 2 plus 2, 4, 2 plus 2, 4, and this is also 5. So that is A multiplied by A itself. And then here I multiply alpha, which is a number in all entries based on the previous lessons. And then I will also multiply beta in all entries, but of course these are 0, so this remains 0. And then I know how to add matrices, so I copy and paste the left side. And then I add entry by entry, so it becomes alpha plus beta, 2 alpha plus 0, 2 alpha plus 0, and alpha plus beta. So in order to establish this, alpha plus beta that appears here and there should be equal to the number 5, and 2 alpha should be 4. So I will actually have a system of equations now that alpha plus beta is 5, 2 alpha is 4. From here I get alpha is 2, and then when I put it back here I will get beta is 3. So alpha should be 2, beta should be 3 in order for that relation holds. Yes? So what about the next problem? The next problem is actually not hard. What you can do, you can start multiplying this matrix by itself 3 times, and then go and read the entry on the third row and second column. It becomes something in terms of x, and take that one and equate it to 72 and solve that equation. This is possible, but the reason that I brought this example is that because whenever you are interested in one particular entry, my preference is not to do the whole calculation, because the whole calculation will reveal all the entries. But we are not interested in the 9 entries at the end. I'm only interested in the entries of which is sitting on the third row and the second column. So what I do, for example, I would say that I am interested in this. Okay, so I will interpret it in this way. This is the formula that I have given you in one of my previous remarks, but might be we haven't used it so far. I want to use it now. Okay, so a to the power of 3 can be written in the form of a squared times a. But do you remember, if I want to find a particular entry of the product of 2 matrices, I really don't need to calculate the whole product. What I need to do, I will take the third row of the matrix on the left. So the third row, do you remember I showed it with this R sub 3. The third row of a squared multiplied by the second column of a. You remember we had in one of my previous remarks, we talked about these kinds of multiplication, and we had one example just trying to describe it. But here in practice we are using it. So if I am interested in finding the entry on the third row second column, I can take the third row from the matrix on the left and just multiply it by the second column of the matrix sitting on the right. But a squared can also be viewed as a product. It is a product, yes? So the third row of a squared, I can write it like this, and then multiply it by the second column of a. Of course, I am explaining, it seems that I am writing the same amount of thing, but I'm trying to explain it. This is why it seems lengthy, but this is more efficient to do. Okay, but now can you tell me, I had also another formula, I don't know if you remember. If I am interested only in the third row of a matrix, of a product, what I'm supposed to do? I will take the third row of the matrix on the left and multiply it by the entire matrix on the right, and then this. at least I want you to understand why we can write this in that form. So in order to find the entry on the third row, second column of the matrix to power 3, I only need to take the third row of A, multiply it by the whole A, and just multiply it by the second column of A. This will give me the entry that I need, okay? Okay, so this, I will do it here. So you see here, we know that this number is 72. This is given to be 72. So 72 is equal to, here you have the third row of A, which I can read it immediately. It is x minus x. And then I multiply it by the whole matrix, x minus x, x minus x, x, and x, minus x, and then I have x minus x and x. And then I multiply it by the second column of A, which is this matrix. Of course, if you are patient, you can multiply matrix by itself in its entirety 3 times and then calculate. But then you are actually spending time on something we don't need. Okay, so if you don't mind, I keep this x minus xx. I do first this multiplication. This is 3 by 3 matrix. This is 3 by 1 matrix. So the answer will be a 3 by 1 matrix. So let us do the calculations in our head. I take this row and multiply it here. The first one times the first one gives me minus x squared. This will also give me minus x squared. This will also give me minus x squared. So if I add them up, it is minus 3x squared. And I will take this and multiply it here. This will give me positive x squared, positive x squared, positive x squared. If I add them up, it becomes positive 3x squared. And the third one is more or less, it's exactly, not more or less, it's exactly the same as before, so it becomes minus 3x squared. And then I take this row and multiply it by this column. This is 1 by 3 matrix. This is 3 by 1 matrix. So as you expected, you get a 1 by 1 matrix, which is the number itself. So this multiplied there, it's minus 3x cubed. This multiplied there is again minus 3x cubed. This multiplied there, it's minus 3x cubed. So it is minus 9 3x, so minus 9x cubed. So 72 is equal to minus 9x cubed. So minus 9x cubed is 72. So this means that x cubed is minus 8. So this means that x is negative 2. Yes? Okay, I want to actually talk about another type of problems. I just want to solve one of them for you, and then we actually end the lesson here. Then I am able to make a quiz for you, and of course I will give you a little bit of time so that you can enjoy your holidays, and then you still have enough time to work on. So another type of problems that I am interested now are, for example, examples like example 111. So let A, B, and B be square matrices of the same order such that AB plus BA is equal to the 0 matrix. We want to show that A squared B is equal to BA squared. Actually, I am really interested in these kinds of problems because here you really need to know the rules that are actually matrices are enjoying them, yes? Because you see, there are no calculations involved here. I don't know the matrices A and B. What I want to prove, so let me go to the board here. So what I know is this. Someone tells me that there is a pair of matrices A and B. Which pair I really don't know, but I know that for that pair, this sum is the 0 matrix. Only based on this assumption, I am supposed to prove that A squared B is equal to BA squared. Yes? How can I prove this? So is that understandable? So if I ask you to show this, I haven't given you the matrices, so you cannot start multiplying given matrices. So this is important. These kinds of questions are very important from theoretical point of view because it actually provides you the opportunity to learn the properties that the matrices are following. Is the question clear? Okay. So we want to show that if I have a pair of matrices that satisfy this relation, that pair will also satisfy this relation. So in other words, a squared commutes with b, because you see that I am interchanging them, okay? In numbers, this is completely trivial. No one tries to prove these for numbers because it is completely trivial. We can interchange, but there is no guarantee that I can interchange them. And I haven't mentioned anything about interchangeability here. I have just given you that AB plus BA is the zero matrix. So this is a very, very simple exercise, of course, but I want you to get used to this way of exercises as well. So do you have any suggestions? How can I use this fact to prove that is true? Yes?
Maybe, I don't know if you're allowed to do it, but a squared is of course a times a, so it would be a times b, so you could like group them together. So.
Okay, but this is already grouped. Yeah, these kinds of things are actually exactly the things that I want you to describe. But this is not helpful because what you are doing, you are opening it up and grouping it again. Okay, how can I use this?
Like if you group a, b together, like in parentheses.
Okay, so that I agree with you. So for example, you start from the left-hand side. You say that, okay, a squared b means a times b. Everyone agrees that. And now, so this is why this is true. This is just a definition of a squared we learned today. And what Rocco is mentioning is that I can take these pair of brackets and put them around the second pair. That is associativity. I want you to understand that I don't expect you to write them down, but I want you to understand which properties I am using. Yes? So that's good. Okay, then what? So somehow you need to use this assumption. Okay, so let us understand something about this assumption. If AB plus BA is equal to the zero matrix, we learned that we can do this. I can move this matrix from the left to the right. What will happen? This becomes AB. If I move it to the other side, it becomes the zero matrix minus BA, but 0 minus BA is nothing except minus BA itself. Yes? So here, instead of AB, what can I write? Minus BA. Agree? And I hope that now you see that this minus sign is negative value, so I can pull it out. So this becomes A, B, A. It's good, by the way. You see what happened? I had two A's on the left side of B, but I was able to move one of them to the other side with this rule. But this is not enough because I want to have both of them on the other side. So I will use this idea once more. Yes? So what do I mean? I can use associativity and group them in this form. So I took the pair of brackets from here and put them around there. But then what can I write for BA again? Okay, AB is minus BA, so BA is minus AB. Yes? If AB is minus BA, BA is minus AB. So instead of BA, instead of AB, I put minus, I am missing things, yes? It's not working, is it?
I think it's working.
I'm confused, so I just took this out. Okay, sorry, I have to replace, yes, that's working. Instead of AB, I put minus BA. Yes?
Why did you write AB and then A on the other side?
So I have started, let me explain again. I have started from here. And then because of associativity, I am allowed to move this pair of brackets around the second pair.
Yeah.
And instead of AB, I put minus BA because of my assumption.
Yeah.
And this minus sign is -1 actually, so it floats around. We had about these rules. So I might pull -1A out, and ABA is left, yes? And then again, I use associativity once more, and then remove the pair of brackets around and put them around the first pair, yes? And then AB is minus BA. Yes, I'm using that factor. But then what happens? This minus sign will cancel that minus sign. And then I am allowed to use associativity once more to write B, and then I write AA. And then AA is A squared. And this is exactly equal to the right-hand side. So this is very important from theoretical point of view. This provides a good opportunity to learn the rules that you are using. So you see that what I am using, I am just using associativity, I don't know, three times, I think, yes. I use associativity here, yes, and then here, and then once or three times, yes. So using associativity 3 times, I was able to show that if this is true, this is also true. So these kinds of exercises I want you to also learn. Okay, so I will actually stop the lesson here, but I will now it is enough. So because I will have I wanted to have 10 questions for the quiz. Now I can design them, but you don't need to be worried about your holidays. And then after that, you will start working on them. Yes.
How much time will you give us for the quiz?
I will start doing it on a weekend, but I don't expect you to do it on your holidays. But probably I will give you 1 extra week after that, and then, yeah, 2 weeks probably. Any questions? Thank you.